Alright, so we're going to look at problem. Everything's going crooked on me here. See if I can write straight here. Problem 1.23. There we go. Problem 1.23. Now in this, we are estimating how many subatomic particles are in different things. Now, we're doing this because a proton and a neutron are approximately each on the order of 10 to the negative 27th kilograms. Electrons are on the order of 10 to the negative 30th kilograms. So the protons and neutrons make up a large quantity of the mass 99.9%. So we're going to ignore the electrons and the mass here. And so we're going to count particles. So one particle, proton or neutron, so I'll just put 1p, is equal to 10 to the negative 27th kilograms. So at the beginning of what's going to be a conversion factor to get a number of particles out. So for part A, they want us to figure out the total number of protons and neutrons in a bacterium. Well, it tells us that one bacterium is 10 getting crooked here, 10 to the negative 15th kilograms. 10 to the negative 15th kilograms. Now if I turn this into a conversion factor, one of my proton-neutron particle counts, proton neutrons 1, 10 to the negative 27th kilograms. Well, what's nice is these are all the same base. So we're just looking at our rules of exponents. So I have 10 to the negative 15th on the top, 10 to the negative 27th on the bottom. So my rules of exponents say negative 15 minus 27, or 10 to the 12th. But it's particles, so protons and neutrons. If we're being pedantic, as for what we're actually saying, didn't need to list that. And so the number of protons and neutrons in a bacterium is about 10 to the 12th. Not quite a mole of protons and neutrons. I find that moles, even though we use them in chemistry a lot, they're actually a thermodynamic unit. And so a mole is a valid unit. Now for part B, it wants us to look up how many protons and neutrons are in a DNA molecule. Same thing, we go to our little chart, and DNA has 10 to the negative 17th kilograms. I use the same conversion, 10 to the negative 27th kilograms. And using my conversion rules, so negative 17 minus 27, that becomes 10 to the 10th protons and neutrons. So this whole thing is set up for us to estimate by using our rules of exponents. And so we get 10 to the 10th protons and neutrons in a DNA molecule. So part C, we're going to continue our estimation here. If I can write a letter that looks like a C. C. All right. And for part C, it's how many protons and neutrons are in the human body. Well, most people are on the order of just under 100 kilograms, so an average. Again, I'm going to keep this as a conversion factor. P stands for my particles, but I get to use my rules of exponents. So 2 minus 27 gives us 10 to the 29th protons and neutrons. So we're actually starting to get above a mole. Starting to get a large quantity of protons and neutrons. And the last is to estimate how many protons and neutrons are in our galaxy. And that's something when we're looking for dark matter, when we're looking for these things out there. There are subatomic particles that we try to count by the mass seen. And so let's look at our galaxy. It has 10 to the 41st kilograms. And if it's made up mostly of protons and neutrons, and this is the light matter, the stuff we see. So using my rules of exponents, 41 minus 27 gives you 10 to the 68th protons and neutrons in the galaxy. I definitely would not want to be tasked with counting all of those. And this is how order of magnitude estimates work. You're looking for roughly how many 10 to the somethings you have, and that way your rules of exponents can let you do the estimate. And then, well, if my answer's 9 or 8 times 10 to the 67th, hey, that's good for the number of protons and neutrons in the galaxy. Or if it's 4 to 5 times 10 to the 68th, you're within the order of magnitude. You're near the number because we haven't included the exact figures in the front. And for setting up a problem or for looking at how we're going to measure something, order of magnitude estimates are a good way to start.